god, I thought you guys could see my screen. Why did anyone say anything? Oh my god. Okay, here's what I'm writing. I hate myself. Oh no. No. Okay, alright. Oh god, let's start all over. I hate it. I hate it so much. I hate this. Okay. Okay, let's start all over. I'm not gonna rewrite everything. I'm just gonna let it play there. Let's just look at this for a second. Okay. Number 21 limits to infinity. Okay. We have limit of a function as do we see the mouse now, the pointing? Okay. Thank you. Limit as x approaches positive infinity. That means, of course, infinitely to the right. Limit as f of x as x approaches negative infinity as it points to the left. Okay. Here's a very basic function. F of x equals 1/2 x plus 2. Oh, good. I have to upload this too. Anyway, here is the red line, which represents the function. Just using your finger as we take our finger, pretend my mouse is the finger. As we go infinitely to the right, the function just keeps going. It's not approaching anything. So there are two ways to answer this. Probably for this class, it does not exist. It just keeps going and going and going. It's not approaching anything. It's not limited to anything, hence the word limits. What is the answer to the second limit? Now, there's a feature here where you could raise your hand. I don't know why I don't see everyone. Oh, okay. Where's the Anyone want to tell me what the answer to the next question is? Right here. Just type it in the chat. What is the limit as x approaches negative infinity? -4. Let's see. Going negative infinity to the left, the function is just going down, 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 down. Does not exist. Another way to answer it is this would also be positive infinity. This would be negative infinity because as we're going infinitely to the right, the function is just going to positive infinity, which also technically means does not exist. Um, it's kind of like the universe being infinite. Like we can't get to the end, so we technically don't know if the end exists or not. That's kind of too deep thinking for a math lesson, but essentially this is what this means. I can always go back to that whiteboard later. Whoa, wait, templates? No. No. Get out. I don't want to use this. No, what is going on? No. Delete. Delete. Create new whiteboard. I don't want to use a template. Okay. Okay. There's a function. Now, there was a time in this class where we learned how to actually graph this thing. We actually learned how to graph it last year too. Ooh, this is also a parent function. But a lot of you are like, Mr. Viernes, we don't have the big poster of parent functions right now. It's okay, I'll help you. The graph of this looks like this. And we know something special about this is that it has two asymptotes, like so. Okay. Now, let's answer the question now. What is the limit as x approaches positive infinity? Now, let's think about what we're doing. Here's positive infinity means going to the right infinitely. As we trace our finger infinitely to the right, does it appear that the function is approaching something, or does it not exist? As it goes infinitely to the right, remember there's an asymptote here. What does the function look like it's approaching? Oh yeah, 0. Okay, CP. What is the limit as x approaches negative infinity of the same function? You're on the spot, CP. Hey, it's still 0. Woohoo. Now, there's something actually much more secret going on here. But for now, let's keep that on the back burner. Here we have the limit of x approaches infinity. Let's go x squared. Now, you probably should not even need to graph this. Just think about it. What is that? It's a quadratic. Yes, it's a quadratic. Of course, what we mean by that is a parabola. If we imagine a parabola going infinitely to the right, as in increasingly, you know that the parabola is just going infinitely up. So I don't even need to draw it. Of course, you can. This does not exist. Either answer is okay for me. Because if we draw it, it's going infinitely to the right. Anybody know the answer? Works for me. Now, you might be thinking most of these seem like they're infinity. Well, in essence, sort of. Let's go back over here. Something a little bit more complicated. Now, let's pretend for a moment that this is we don't have a graphing calculator, and let's just graph it from what we remember several months ago. When you had to graph this, you had to find something called the vertical asymptotes. You had to find something called the horizontal asymptotes. You also had to find something called the x-intercepts and the y-intercepts. And honestly, for our purposes, this is all we need. This was several months ago. And I apologize that I'm not writing straight here. Okay. So let's proceed to do this. From what we know, is that the vertical asymptotes are the numbers that make the denominator equal to 0. Hence, we have one at 1. Ooh, I don't like the horizontal asymptotes. Let's save that for last. X-intercepts, it makes the numerator equal to 0. Hence, 0, 0. Y-intercepts is when we plug in 0. Oh my goodness, we still get 0, 0. So right now we have a point here at 0, 0 and a vertical asymptote at 1. Horizontal asymptote. There were 3 features of this. It's when the degree of that we have 3 scenarios where the degree of the numerator is either greater than the denominator, or they're equal, or the degree is less than. The numerator is less than the denominator. There were 3 different scenarios here. In this case here, the degree on the numerator is 1, and the degree on the denominator is also 1. So we have the scenario of which the degrees are equal. So what that meant is we take 2 divided by 1, which gives us 2. What is the horizontal asymptote if the uh if the denominator is bigger? Does anyone remember? If the denominator is bigger than the numerator, what is the horizontal asymptote now? Nobody remembers. 0. If the denominator is bigger on the bottom, it is 0. And if the numerator is bigger on top, it does not exist. Hint, 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 hint. Hint, hint. So we graph this, and we have a horizontal. Crap. No. Undo, undo, undo. We have a horizontal asymptote at 2. And essentially, it looks like this. Oh my god, Mr. Beard. Okay, I got it. Okay. So we can ask ourselves the question, what is the limit as x approaches positive infinity of f of x equals the limit of as x approaches negative infinity f of x? Here's a hint. They're the same answer. Okay. Thank you, 2. They're both 2. You can see with my mouse, infinitely to the right, the arrows are closely approaching 2, and going to the left are closely approaching 2 infinitely as we go left. So there is a big conclusion that can be made here, and I will now write that down. Essentially, these are the same thing. Horizontal asymptotes essentially means that we're asking the question, what is the limits of the function as x approaches infinity? So when we go ask questions like this, x approaches infinity um, of x to the third, we ask ourselves, does it even have an HA? And it doesn't. We know what x cubed looks like. Conceptually, x cubed just infinitely goes up, and graphically, it doesn't even have a horizontal asymptote because it's not even a rational function. So immediately, I would write either plus infinity or does not exist. Really, I like writing does not exist because you acknowledge that, hey, this doesn't even have a horizontal asymptote. X approaches infinity of 3x squared plus 2 over 4x to the third. And I ask myself a question. Does this even have a HA? And we go back and look at our notes from long ago, but I'm going to write it down again. We notice that the degree on the bottom is bigger. So it does have a horizontal asymptote. In fact, the HA here is 0. Hence, my answer is 0. So let's break that down again. Remember, we're talking about the degree. The degree. If the numerator can either be greater than the denominator, they can be equal. They can also be, the degree can be less than, no, greater, no. What am I trying to write? Less than, there we go. Okay. The numerator being greater than the degree of the denominator does not exist. The numerator equaling the degree. This is the front coefficient divided by the bottom coefficient. I should write this better. Let's call it, yeah, call it AN and BN actually. Ratio of front coefficients. And I'll give an example of that in a second. We just did that, but I'll do another one. And this final last one is 0. So going to example C, let's say the limits as x approaches infinity of 4x squared minus 3x plus 1 all over 12x squared minus 1000. It really doesn't matter what those numbers are. All we honestly care about is the horizontal asymptote if it exists. If it has one, that is your limit. If it doesn't have one, for this class, it's 100% going to be does not exist. There are more complicated situations. This is not Calc AB. This is not Calc BC. So we're not even going to talk about it. For the most part, again, this relationship right here, the horizontal asymptotes are basically represented by the limit of the function approaching infinity to the right or to the left. They can be different in more complicated situations, but for the most part, this, let me do it. Actually, let's do it in rainbow. Ew, look at, ew, I don't like it. Oh no. Okay. In your homework, you might get something a little bit more complicated. Oh, actually, sorry. What's the answer to this? Again, you don't even care about this negative 3x plus 1 minus 1,000. We're only caring about the degrees right here. Because this does have an HA. The limit is... It's one of those, CP. They can't be both. 1/3. 4/12 is 1/3. Here, again, the degrees are the same. Here, the numerator is less than the denominator. Here, technically, the numerator is greater than the denominator. Over here, you have x to the third. Ooh. The degree of the bottom of this x to the third has a degree. It's 0. So technically it is bigger. Let's get to something a little bit more complicated. The limits, let's call this example D, of, I believe your homework gives you something like this: 1 over x squared minus 4. X approaches infinity. So you can actually calculate the limits separately. The limit of x approaches 1 over x squared minus the limits of x approaches infinity 4. Because I can do this limit very easily. What is the limits of x approaches infinity of 1 over x squared? Well, do I have any of these scenarios? And you should say, hey, yes, we have the scenario of which the denominator is bigger than the numerator. So this limit is just 0 minus what? Now you have two faces. Thank you. I just took it off. I removed it from the screen. So now we have 0 minus the limit as x is infinity of 4. What in the world is that? The limit as x approaches infinity of just 4. This was actually on our notes, if you, or the one of the lesson videos that tells us exactly what this limit is. Some of you guys are like, I didn't watch it. Well, I'm hoping you will watch it. What is the limit as x approaches infinity of just a number 4? Any guesses? Just give me a wild guess. What is the limit of just a number 4 as x approaches infinity? 4. It is just 4. Let's take a look at this on a graph. Here's what the function 4 looks like. As x approaches a positive infinity to the right, the function still is 4. So not only is it approaching 4, it just stays 4 the whole time. Also, in your notes there, it just says the limit note. I'll write it here again. The limits as x approaches anything of a number is equal to the number. I wrote that on the last note, so I'm going to write it again here. Actually, I forget. It was 19 or 20. I forget which one it was. So my answer, 0 minus 4 is negative 4 is the answer. Example, and we have limits as x approaches infinity. This is 2x squared minus 6 all over parentheses x minus 1 squared. Ooh, I know the answer already. I really just looked at this problem in my book, and I immediately know the answer. Not that I'm smart or anything, I just see it. I'm just seeing if anyone knows it too without working it out. 2! How fast? Thank you, participants. Now, let's understand why it was quickly 2. I'm guessing that you could predictably predict that this says this remains 2x squared. If we had to multiply this out in our head, we would get x squared minus 2x plus 1. And we go, hey, the degrees are equal. So according to this, it's the ratio of 2 over 1. Of course, it's just 2. Did I cover that? I covered that. 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 Okay. What else is in tonight's homework? 1 through 41. What's 41 say? Ooh, those are good questions. I'll leave it to you guys. One last thing. I guess this is a theorem. Limit f of x exists if and only if this is true. Also, actually, no, only this. What this essentially means is if the limit can only exist is if the limit approaching from the left and the right, and the reason why I have this plus sign because it means to the right and from the left, they have to be equal. So here's what I mean. This is a weird function that has 2 intercepts and 2 asymptotes. Technically, this limit would not exist as x approaches infinity, since as to the left negative infinity, it's approaching something else to the positive infinity. This technically would not exist because they both have to approach the same thing from both sides. And it applies to anything else where, let's say, we are approaching this. We talked about this before we left, and I call this number 2. This also does not exist because as you approach a number from the right 2 and to the from the left 2, they're approaching 2 different numbers. They have to be exactly the same. Now, here's a really good true or false question. True or false? This is going into deeper calculus questions. True or false? The limit exists if and only if the point exists. And I'll leave it at that for you guys to think about. Tonight's homework does have some true or false questions, and I can go ahead and talk about them next time. But this is basically the end of the lesson.